From the depths of the universe, the metal courier had returned, having witnessed planets collapsing and stars shattering. It had skimmed past supermassive black holes, raced beyond quasar jets that devoured galaxies. It had crossed light years of nothingness and caught a glimmer at the edge of the cosmos. Chasing that glimmer, the metal courier had locked onto its target, not knowing where it would lead. And now, after an epic journey of 4 billion years, the probe had finally come home. But the home it found was not the blue dot it remembered. The sun had swollen into a red giant, grotesque and violent. Mercury and Venus were gone, as if they had never existed. Earth, if it could still be called Earth, was nothing more than a fractured mass of iron and nickel orbiting perilously close to a dying star. Once overflowing with life, sheltering thousands of souls, the blue planet had lost its own. Now in pale and faded hues, it stood as a silent witness to the cosmic graveyard.
What had happened to Batuta's home, the blue planet? If you're ready to witness the depths of the universe like never before on Batuta's journey, hit the like button and subscribe. The revelation begins now.
Humanity had dwindled to barely 100 million souls, finding a new home on Europa. The heat of the red sun had long since melted the moon's ice, and now this small moon of Jupiter was the only refuge they could reach. It took the probe only a few minutes to decipher the radio signals sent in a strange tongue. Even in the last stronghold where they clung to life, humankind was still defying the universe, sending messages into the void, waiting for something to answer, as if yearning to hear they were not alone. Those who remained were filled with curiosity, a curiosity tinged with hope. They still remembered the probe, despite it having been launched in the distant past. Somehow, the memory of the event had been miraculously preserved across the ages. Humanity, they said, had tried again and again to spread across the galaxy, but every colonial attempt had ended in failure. They could send machines into interstellar space, but whenever they tried to cross the vast emptiness between the stars themselves, their fragile bodies betrayed them. At least for humanity's physical limits, this was true. But the spacecraft had brought back unseen beauty, unknown secrets, and visions of what lay beyond the edge of the universe, delivering them straight to humanity's doorstep. Sometimes, assembling visuals to match what it described was difficult. But, over the course of its interstellar journey, the probe had learned how to overcome that challenge. From the micro-world to the vast macrocosm, everything was stored in the memory of this metal wanderer. Amid cold mathematical data, the search for warm human meaning continued, and each discovery brought with it new questions. The images locked within the probe's memory were capable of overshadowing even the wildest science fiction humanity had ever imagined. Every vision that stretched the limits of human imagination was proof of how vast the universe truly was, and that there was more than they had ever dared to think. Regions where supermassive black holes danced in galactic cores, auroras shimmering in the magnetospheres of neutron stars, the first light of young stars being born inside nebulae. All of it passed through the probe's electronic eyes and was now transmitted to the last representatives of humanity. On Europa's icy surface, inside research stations, scientists studied the data, their hands trembling as they examined holographic projections. Every new piece of information slightly increased their hope of. In theory, this information could open the door to interstellar travel for humanity. Yet, with Europa's limited resources, bringing such technologies to life remained an immense challenge. The probe's story was also a chronicle of solitude. For 4 billion years, it had traveled alone through the cold darkness of the universe. A shattering experience, even for an artificial intelligence. In the end, even this satellite of metal could feel the universal ache of isolation it carried across the cosmos. The probe had overcome this loneliness only by doing science, by exploring and learning. Each new discovery reminded it of the meaning of life and existence.
This grand account was not merely a scientific report, but also the story of humanity's search to understand its place in the universe. Every observation the probe made emphasized both the vastness of the cosmos and the uniqueness of humanity. For the last humans trapped on Europa, this story offered both a merciless truth and boundless hope. For these people, physically no different from cosmic dust, every piece of data they uncovered was proof of how small they were, and yet how great they could be. And now, the metal carrier had finally returned home, not only laden with knowledge, but also carrying hope. Every word it transmitted had the potential to change the fate of the last humans living in Europa's icy subsurface oceans. Perhaps this lonely wanderer, who had unraveled the universe's secrets, could truly show humanity a way out. The probe had begun to speak, and the deepest secrets of the cosmos were now reaching the ears of the last humans on Europa. Its first mission parameter was clear: to cross the boundaries of the solar system and step into interstellar space. This journey was only the beginning.
When it named itself Batuta, it had drawn inspiration from the great 14th century explorer Ibn Batuta. Over the course of 3 decades, this legendary traveler had journeyed across the entire known Islamic world, covering roughly 117,000 kilometers, surpassing even other great explorers like Marco Polo and Zhang He. Bearing his name seemed fitting for the probe. In the past, these names had pushed the boundaries of science, and now, through metal and silicon, they were pushing the boundaries of the universe's depths. This was why Batuta was the perfect name for this space career. The spacecraft knew such a name would suit it well as it set out into the infinite black. But before it could escape the solar system, it had to undergo a series of tests. It had thousands of siblings, each as intelligent and capable as itself. Only a chosen few would earn the privilege of fully independent thought and autonomous action, free from human control. Those who failed would remain trapped within the solar system forever. In this vast cosmic gladiator arena, only the strongest could survive and earn the right to return home. Batuta had to prove to its human creators that it could endure the harsh conditions it would encounter in the wide universe, and that it could design ingenious experiments to unlock nature's most closely guarded secrets. And so, it began its trials on Titan, Saturn's largest moon, a world filled with magnificent mysteries. Titan had been discovered in 1655 by pioneering astronomer Christian Huygens using a homemade telescope. Huygens himself was a key figure in the emerging scientific revolution and one of the first to investigate, scientifically, the possibility of life on other worlds. The perspective of this Dutch scientist would reach into the future. Every time Huygens turned the lens of his telescope to the sky, he was in truth gazing toward humanity's future. Some planets may indeed harbor various kinds of rational creatures, differing in degrees of intellect and feeling, he had written. Huygens had little idea that Titan itself would one day become such a candidate. Centuries later, humanity would reach a major milestone in space exploration on that very moon. In 2005, a small probe less than 3 meters wide separated from the port-side attachment hardware of the Cassini spacecraft. Cassini had spent nearly 7 years on its journey to Saturn, and it took the probe an additional 22 days to travel from Cassini's orbit to Titan. This craft, bearing the name Huygens, used a parachute to slow its descent as it passed through Titan's atmosphere. This was only possible because, among all the worlds in the solar system, Titan was the only solid body besides Earth and Venus to possess a significant atmosphere. If this distant world contained oxygen and hydrogen, it could hold the promise of life for humanity. For that reason, Huygens touched down gently, skidding across the icy surface after carving a small depression, bouncing until it came to rest. It was the first time a human-made representative had touched the surface of a world in the outer solar system. For Batuta, Huygens was a true pioneer. and the world it touched was unlike anything humanity had ever encountered before. 50% larger than Earth's moon and 80% more massive, Titan was titanic in every sense. Its core was composed mainly of rock, but its crust was made of ice. Surrounding it was an atmosphere even denser than Earth's, increasing the surface air pressure by roughly 50%. Could the human body physically withstand that atmospheric pressure? Was Titan the ideal world we had been searching for? Titan was a beautiful, ghostly, and mysterious world because it shared something with Earth that every other world in the solar system lacked: liquid. Titan had rivers, currents, bays, deltas, and every other feature associated with surface liquids. You could stand at the edge of a lake, see its shimmering surface stretch beyond the horizon, and feel the sandy grains beneath your feet as waves lapped at your ankles. And all of this was happening at nearly 200 degrees below zero. It was as if the world were locked in an ice age. Nature here seemed to be trying to prepare an environment for life, much like Earth during the Pleistocene epoch, around 2.5 million years ago. The lake before you wasn't filled with water, but with hydrocarbons. The rain falling from the sky wasn't made of water droplets, but was part of a cycle in which methane and ethane evaporated into the atmosphere and then fell back to the surface. Yet, beneath the kilometers-thick icy crust under your feet was a subsurface ocean of liquid water, kept warm by internal heat and kept liquid by the presence of ammonia. In fact, Titan was the only known world with liquid both on its surface and beneath it, making it a fascinating potential home for two very different kinds of alien life. The first was familiar, the kind of life every organism on Earth shared: the use of water as a solvent. Water was the container in which life's chemistry took place. It allowed molecules to mix and recombine. It helped regulate temperature. It brought food close and removed waste, and it helped cells maintain their shape. Water was like a universal language. If you wanted to live, you needed it, and that was true for every living thing. But water wasn't the only liquid. Titan's seas, lakes, and streams of hydrocarbons could serve a similar role. Ethane and methane could act as solvents for a strange kind of biochemistry, one that could function at nearly 200 degrees below zero. Titan was not alone when it came to mysterious underground oceans. Even Saturn's tiny moon Enceladus, just 500 kilometers in diameter, harbored vast oceans. Jupiter's moons Europa, Callisto, and Ganymede likely all contained more liquid water than Earth itself. It seemed we had revealed that our solar system was remarkably suited for life, because most planets in the solar system contained water essential for survival. Even Pluto might have hosted a subsurface ocean, clinging to remnants of internal heat left from radioactive decay in its core. But reaching these oceans was no easy feat. In the frigid temperatures of the outer solar system, far from the sun's light and warmth, water ice was as hard as rock, sealing away worlds like Europa and hiding any possible life within their dark oceans under ice sheets up to 100 kilometers thick. Upcoming missions like the European Space Agency's JUICE, European Icy Moons Explorer, and NASA's Europa Clipper would not attempt to drill through these icy crusts. Instead, they would orbit these worlds and, if conditions allowed, sail through the plumes of cryovolcanoes. Humanity was pushing its technology to the limit in the hope of reaching these distant oceans. Every discovery brought with it a new door of hope for our species. Because icy moons like Europa were not sterile or still. They were active and alive. Their shells groaned and creaked, with massive ice fields grinding against each other. It was a colder, slower version of tectonic activity on Earth. If there was any biological activity in those mysterious oceans, the frozen volcano's plumes could carry its molecular traces. If the right elements could meet in the right concentrations, life might still find a way in those lightless oceans. And these were not the only mysterious interiors in the outer solar system. In this harsh environment, Batuta was testing its scientific methods and proving its worth to its creators. Each experiment turned another mystery into knowledge. With every test, humanity inched closer to its goal. After a century of trials, Batuta finally received permission to leave the solar system. Ahead lay the infinite darkness of interstellar space and the greatest secrets of the universe.
When Batuta's interstellar journey truly began, it faced endless darkness and silence. About halfway through its 100,000-year voyage, the small probe decided to change course. Steering toward a new target 90 light-years from Earth added 8,000 years to the total trip time. But Batuta decided it was worth it. This metal traveler had chosen its own destiny. Perhaps this new route would lead humanity to its goal. The spacecraft was a passionate student of human history, deeply studying the records, books, charts, digital files, and everything its creators had uploaded into its systems. One star in particular caught its attention: Algol, the demon star. 3,200 years ago, the Egyptians had listed it as a star that brought bad luck on unlucky days and good fortune on lucky ones. In Greek mythology, the star represented the severed head of Medusa, held by Perseus for the world to see after his victorious battle. In other words, humanity had tried to explain its fears, dreams, and hopes through cosmic realities. Did cosmic events truly influence humanity? In Chinese astronomy, the star was part of a 5-member burial ground. Among them was a star roughly translated as piled-up corpses. Of course, the star had a more formal scientific name: Beta Persei, the second brightest star in the Perseus constellation. But in the 17th century, when Italian astronomer Gimignano Montanari discovered Algol's mysterious brightness fluctuations, the name took on a new meaning. More than a century later, sharp-eyed astronomers realized this change was periodic. About every 10 days, Algol would suddenly dim for several hours, then return to normal. The cause was discovered in the 1800s by Harvard Observatory astronomer Edward Pickering. This astronomy detective was among the first to decode how stars worked and what they wanted to tell us. Pickering famously hired a team of women, called the Harvard Computers, to analyze stellar spectra. They discovered that Algol's dimming was caused not by one star, but two. A bright, hot primary star orbited by a smaller companion. From our viewpoint, when the companion passed in front of its parent, the whole system appeared dimmer. Although seemingly simple, Algol's configuration revealed a violent history. The two main stars were born together, yet the larger Algol A was still in the main hydrogen-burning phase, while the smaller Algol B was a subgiant nearing the end of its life. But this was the opposite of what it should have been. According to humanity's knowledge, it should have been the other way around, but the universe was a place where age did not guarantee wisdom, and it was open to infinite surprises. Larger stars burn hydrogen faster, so Algol A should have nearly died. The answer to this puzzle was a rather boring process called mass transfer. When Algol B reached the end of its main sequence and expanded to become a red giant, it overflowed the gap between the stars, allowing its companion to steal some hydrogen, like a vampire preying on its own sibling. This cosmic vampire story left a deep impression in Batuta's memory, a universe where even stars fight for survival, where even closest friends exploit each other for energy. It reminded the probe just how complex the universal laws of life and death truly were. But at the most fundamental level, something about the universe was similar to us: the strong survive. Algol was just one of many known multiple star systems. The simplest were binary systems: two stars orbiting a common massive center, or a smaller star orbiting a larger parent. The most complex known systems had as many as 9 stars dancing in intricate, tangled orbits around each other. For example, Alpha Centauri was actually a triple system. 2 stars orbited close together, and because the system was near enough to Earth, backyard telescopes could resolve the pair along with a third,
Proxima, orbiting at a much greater distance. Other arrangements were far less stable, their motions chaotic and unpredictable as they competed gravitationally. But Algol and multiple star systems weren't the only curiosities in our neighborhood of the Milky Way. There was no better place to witness the universe than the ship's deck. On a clear night at sea, with the moon waning, the stars scattered across the sky like a shower of light, revealing their secrets from every direction. The universe was the largest ocean we had ever seen, of which we only knew a tiny fraction, and every star drifting in this ocean was like a new continent waiting to be explored. This was even more vivid in the early 1800s, a time when ships had no electric lights. It's easy to imagine the profound impact such a view would have had on a young, curious mind far from home and hungry for knowledge. Born in 1784 in Minden, then part of the Kingdom of Prussia, Friedrich Bessel was no typical astronomer. He dropped out of school at age 14, repelled by Latin, and went to work in an import-export business. But his proximity to shipping and time spent around sea vessels sparked a curiosity about navigation, which in turn drew him to astronomy. Mathematics was everywhere in the universe, and the nature of math itself fueled curiosity. This was true for Bessel. At first, he channeled this interest into commerce, but soon mathematics carried him to far greater heights, turning Bessel's eyes toward the cosmos.
It wasn't long before his natural talent was recognized, especially after he made successful measurements of a comet. Then he faced a choice: a relatively comfortable life in trade, or a less comfortable one as an assistant at a private observatory. He chose the stars. His target was 61 Cygni, the flying star of classical astronomy, named for its apparent speed across Earth's sky. He aimed at 61 Cygni because he correctly guessed that its rapid apparent motion was a clue that it was closer to Earth than other stars, making it a good candidate to measure distance. But when he finally calculated the distance, it was so enormous that he had to invent a new unit of measurement to describe it. He could have used miles, kilometers, or even multiples of the distance between Earth and the Sun. But all of these conventions resulted in annoyingly large numbers. So he created a new term, the light year, the distance light travels in 1 year. Bessel's curiosity was so great that he didn't just measure distance. He created a new language to help humanity grasp the cosmic scale. With this new terminology in hand, he could explain the distance to 61 Cygni, exactly 10 light years from Earth. But 61 Cygni wasn't the closest or the strangest star near Earth, not close by any means. For example, Betelgeuse, the 10th brightest star in the sky, was about 450 light years away. Despite that vast distance, Betelgeuse was both massive and a giant. It weighed at least 15 times the mass of the Sun and had an almost unparalleled diameter, more than 750 times wider. If placed in our solar system, it would engulf Mercury, Venus, Earth, Mars, and most of the asteroid belt. Indeed, Betelgeuse was so swollen and distorted that it was no longer a sphere. Astronomical imaging revealed a swollen surface bubbling with underlying chaos. In late 2019, the star unexpectedly dimmed, dropping from the top 10 brightest stars in the sky to 20th place. It was as if Betelgeuse had suffered a cosmic heart attack. Its soul briefly separated from its body, and when it returned, it never regained its former brilliance. The sudden dimming was most likely caused by an intensely heated plasma cloud ejected by the star into space. As the cloud cooled, it formed an orbiting dust veil that temporarily hid Betelgeuse's brightness. After the debris cleared, Betelgeuse returned to its former glory.
However, Betelgeuse would not last much longer. It was expected to end its life soon, probably within the next 100,000 years, in a colossal supernova explosion. Theoretical calculations predicted it would shine as brightly as a half-moon at its peak, outshining all other stars and planets in the night sky. It would be an intense, almost uncomfortable point of light. Whether humanity would still be alive then was uncertain, but it would provide enough illumination to read a book comfortably in the middle of the night. And yet within weeks, it would fade into irrelevance, no longer visible to the naked eye, and Orion would stand in the night sky, missing one of its shoulders. Most stars, however, were not giants. They were either medium-sized stars like the Sun or smaller red dwarfs. This included Proxima Centauri, the closest star to the solar system, visible only with a telescope. The star itself was quite ordinary, except for one thing. It carried a planet. This distant world's discovery raised yet another question. Was there life there? Thanks to an observational campaign known as the Pale Red Dot Initiative, a tribute to the mesmerizing pale blue dot image taken by Voyager 1 at the distant edge of our solar system, we now know that the planet called Proxima b offers the closest chance for life to find a home beyond our solar system. Of course, nothing is guaranteed yet, as our telescopes aren't powerful enough to even confirm the presence of life's prerequisites, like liquid water or a stable atmosphere. To sustain habitability, planets need to orbit close to their parent stars. In Proxima b's case, this world circles its star within just 0.05 astronomical units, much closer than Mercury is to the Sun. This is because red dwarfs emit much weaker light, and only at such close distances can a planet receive enough heat to remain potentially habitable. But if life did take hold there, it wouldn't be easy. Red dwarf stars are especially temperamental, prone to star spots covering half their surface at once, and sudden outbursts of plasma electromagnetic storms flooding their local environment. Planets like Proxima b swing between extreme cold periods and intense radiation bursts. Life on Proxima b would be harsh. Living there would be like defying the devil. We would be brave warriors fighting against brutal natural disasters and radiation storms, and maybe only a small minority of us would survive. And on top of that, Proxima b was most likely tidally locked, meaning one side of the planet always faced its star. This meant that Proxima never set or rose on the planet, leaving one half locked in eternal night, while the other half basked in perpetual daylight. But this curious situation didn't automatically mean a dead world. Computer models showed that even these planets could sustain life. The key was having enough water and atmosphere to circulate heat around the entire planet, so the day side wouldn't scorch under the star's glare, and the night side's atmosphere wouldn't freeze and catastrophically collapse. The most fragile yet fascinating scenario was what sci-fi writer Arthur C. Clarke called striped worlds. On these worlds, life could only survive in the Terminator Zone, the twilight region between day and night. The center of the day side would be a blazing desert and the night side a frozen wasteland. But if conditions were just right, a narrow stable band, a thin strip of temperate climate heated from one side and cooled from the other, could circle the planet. Living there would be like walking a tightrope, but if there was even the smallest chance of life beyond Earth, it was worth exploring, because we knew Earth's end day would come.
And so Proxima b was just the beginning. The galaxy held an endless variety of worlds. The lowest estimates said about one planet per star, meaning there were at least hundreds of billions of planets just in the Milky Way. The high end suggested trillions could live in our galaxy alone. There were definitely solar system copies, 4 rocky inner worlds, and 4 giants. But there were also much stranger arrangements, like the TRAPPIST-1 system, with 7 rocky planets orbiting close to their parent star, 3 of which were in the habitable zone. The universe seemed like a master architect with boundless creativity. Each system was designed as a flawless masterpiece in itself. There were giant planets so close to their stars that they were actively being destroyed. There were super-Earths and mini-Neptunes, planets surrounded by thick hydrogen clouds with water-covered surfaces, Hycean worlds. Worlds so hot they glowed, and worlds completely covered in ice. And even rogue planets cast into darkness with no system to call home. Of course, Batuta could never hope to catalog them all. So after its 10,000-year brief detour to the Algol system, it returned to its planned orbit, visiting a series of star systems. As the spacecraft passed through the Orion Arm and headed toward the galactic core, it knew there wasn't much to learn during the first million years of its journey. No signs of life or exotic physical collapses were found here. For that, it would have to venture deeper into the core of the Milky Way and beyond.
After Batuta's 10 million-year journey, the moment it finally reached the outskirts of the Milky Way's core was a cosmic triumph. The galaxy's core was an elongated bar, and the spacecraft found itself just beyond the inner arm. Reaching this point hadn't been easy, but Batuta suspected it wasn't the first craft to venture this deep. Batuta was searching for traces of those who had come before. It had accepted the silent and arduous battle to reach the heart of the universe. Somewhere within the Norma Arm, about 5,000 light-years from the edge, the spacecraft detected a faint, intermittent radio signal. At first, it thought it was just another pulsar, but the spectral signature of the radio mission didn't match. Upon closer inspection, the flickering rhythm was all too familiar. It was artificial, a signal of the kind Batuta itself would create. This discovery sparked a strange feeling of companionship within the metal heart of the probe. And so, Batuta designed its own calling card. By carefully manipulating a dead system for 10,000 years, it caused all the rocky planets to collide with their primary star, increasing the abundance of heavy elements far beyond what such a star should normally have. In about 20,000 years, humanity and other spacecraft in this corner of the galaxy would notice a sudden and strange spike in these heavy elements polluting the star. Batuta had carved its own path to be noticed, like a street artist leaving graffiti. But the difference was that Batuta did it in the language of the universe. And there, it clearly engraved the message, "I was here." Maybe they would attribute it to a natural phenomenon, or perhaps they would assume it was the machinations of one of their rogue probes. Or maybe, even if they were still there, they wouldn't notice at all. After a journey spanning 10 million years, Batuta finally began to feel its age. Yet, despite everything it had witnessed and experienced so far, it couldn't hold a candle to some of the oldest inhabitants of the galaxy. And Batuta had the honor of encountering a few of them. One of these stars was simply known as Methuselah, named after the biblical figure said to have lived 969 years. More formally, the star was called HD 140283, but it gained fame when astronomers revealed its unexpected age. Some estimates suggested it was likely over 14 billion years old, possibly older than the universe itself. It was the oldest star we knew, a living fossil, the grandfather of stars, telling ancient stories from the dawn of the universe. That's why it quickly became famous. But how could this be possible? Some wondered whether Methuselah's existence challenged our understanding of Big Bang cosmology. Others questioned if it undermined our most fundamental grasp of stellar physics. Regardless, Methuselah was undoubtedly ancient and had much to teach us. Estimating the age of an individual star was difficult. For centuries, astronomers had no clear idea. They only knew that the galaxy held a vast variety of stars. There were mid-sized yellow-white stars like our Sun, small red dwarfs like our nearest neighbor, Proxima Centauri, and then giants came in both blue and red varieties such as Rigel and Betelgeuse. By the late 1800s, astronomers began to think that stars started out large and slowly shrank and cooled over their lifetimes, radiating light during this process.
But a few decades later, Sir Arthur Eddington calculated that if this were true, the maximum age of the Sun could only be a few million years, an embarrassingly short number, inconsistent with the billions of years implied by geology and evolution. These calculations caused a major shock because they created significant inconsistencies within themselves. It was as if we were miscalculating time itself. We began to sense that something was wrong. And so the true keys to stellar evolution finally came from the steady eye of Annie Jump Cannon, one of the famous computers hired at Harvard Observatory, tasked with the repetitive job of sifting through vast amounts of observational data. These computers were initially chosen because they were paid about 25 cents an hour, cheaper than hiring men who cost around $1 an hour. As Cannon systematically classified the spectra of tens of thousands of stars, she realized that stars were not just a random variety. Instead, they followed a specific spectral sequence. She organized them into spectral classes O, B, A, F, G, K, and M, remembered by the mnemonic, "Oh, be a fine girl, kiss me." This classification revealed not only the stars' colors, but also their temperatures and ages. However, what truly captured Batuta's interest were the far more exotic objects it encountered as it approached the galactic core. The supermassive black hole known as Sagittarius A star was a monster sitting at the heart of the Milky Way, weighing in at 4 million solar masses. Around this cosmic giant, stars like S2 danced at incredible speeds. Einstein's theories were being turned into a live performance, like a ballet dancer spinning gracefully on stage. Tracking the orbit of S2 provided one of the most precise tests of Einstein's general theory of relativity. As the star approached its closest point to the black hole, called periastron passage, its light experienced the redshift, and its orbit precession could be observed. These measurements confirmed that space-time truly bends in gravitational fields. During the thousands of years Batuta spent in this region, it studied not only the supermassive black hole, but also the strange objects surrounding it. Magnetars, the most extreme type of neutron stars, possessed magnetic fields so powerful they could literally tear atoms apart. These fields were trillions of times stronger than Earth's magnetic field. Any matter passing close to a magnetar would instantly ionize, as electron orbital energies couldn't overcome the magnetic field's energy. Atoms would elongate into rod-like shapes, making chemistry impossible. All known states of matter were invalid here. The physical laws we understood were shredded and torn apart by these cosmic monsters. Observing these objects from a safe distance, Batuta couldn't help but marvel at how extreme the universe's conditions could be. One of the most fascinating phenomena Batuta encountered in the galactic core was the density of star-forming regions. Giant molecular clouds like Sagittarius B2 were real treasures of chemical complexity. These clouds contained organic molecules such as ethyl alcohol and methylformate in astronomical quantities. As Batuta studied these cosmic distilleries, it discovered that the building blocks of life could emerge in the most unexpected places in the universe. The dense environment of the core also witnessed stellar collisions. While these rare events were nearly impossible in the outer regions, where distances between stars were vast, the core's star density was so high that collisions were relatively common on astronomical timescales. Batuta had the chance to observe the aftermath of such a collision: the merging of two main sequence stars, forming a blue supergiant. The two stars danced together for billions of years before merging, and Batuta was fortunate enough to record this event. Or perhaps it was a gift from the universe. What we do know is that if Batuta hadn't altered its course, it wouldn't have brought us such valuable knowledge. Batuta did the right thing. It had become a detective chasing the universe's secrets and was relentlessly uncovering them.
One of the most mysterious components of the core was dark matter. Batuta detected that there was about 5 times as much dark matter as ordinary matter. Yet this enigmatic substance revealed itself only through gravitational interactions. Dark matter was an invisible scaffold that allowed the galaxy to rotate much faster than the visible mass alone could explain. The probe was equipped with special sensors designed for various dark matter detection experiments. While searching for WIMPs, weakly interacting massive particles, it also tried to detect hypothetical particles like stereo-neutrinos and axions. After years of careful observation, it detected a few suspicious signals, but none were conclusive evidence. Batuta sensed this great mystery. It knew something was happening there, but its physical capabilities could perceive only a fraction of it. One of the most astonishing phenomena Batuta discovered in the core was the behavior of time itself. Near the intense gravitational fields, the flow of time slowed significantly. Comparing the time it spent in orbit close to Sagittarius A star with time in the galaxy's outer regions, Batuta detected a notable difference. This relativistic effect required constant corrections to the probe's internal clocks. Among the most fascinating discoveries was a strange ring-shaped structure surrounding the core. Visible through radio telescopes, this giant ring was formed by the combined effects of supernova explosions and stellar winds. Known as the Fermi bubbles, these structures extended 50,000 light-years above and below the galactic disk. Entranced by the unique beauty of the Milky Way, the Fermi bubbles danced endlessly in response to this grandeur, joining a cosmic dance that will last billions of years. The most dramatic event Batuta witnessed during its time in the core was the tidal disruption of a star by the black hole, a tidal disruption event. The star, cataloged as HD 123456778, approached Sagittarius A star so closely that the black hole's tidal forces literally tore it apart. Some of the star's matter fell into the black hole, while the rest was ejected into space. Observing this event was both a scientific and philosophical experience for Batuta. Watching a star, a sun, that had emitted light and energy for billions of years, perhaps harboring planets and life, be destroyed within hours revealed just how merciless the universe could be. The death of stars drifting through this vast cosmic ocean for billions of years was not merely a physical event. It was like the infinite fading of a light that had guided our path for eons. Would we one day vanish like that star? Before leaving the core, Batuta made one final discovery. Just near Sagittarius A star, it found the strangest object detected so far, a hybrid object named G2. This entity was neither quite a star nor merely a gas cloud, a bizarre hybrid exhibiting characteristics of both. When G2 approached the black hole, its temperature soared to millions of degrees, but contrary to expectations, it did not break apart. This observation became one of the most enigmatic entries in Batuta's database. G2's structure and behavior seemed to challenge known physical laws. The probe recorded that this object might represent an undiscovered form of matter or even a more exotic phenomenon. The millions of years Batuta spent in the core's depths granted it a new understanding of the universe's scale and complexity. Here, physical laws were tested under the most extreme conditions. Space-time distortions, time dilation, quantum effects and relativity, all were parts of everyday reality. The events at the heart of the galaxy were so immense that this place had become the universe's most advanced university for Batuta. Every event brought a new discovery, and each new discovery unveiled another veil of the universe's mysterious secrets. Humanity was learning more, and with every lesson evolving to learn even more. Now it was ready to cross the boundaries of the galaxy. Its next target, the Andromeda Galaxy, and the unknown universe beyond. Because Batuta knew that the real adventure had yet to begin. The Milky Way was only the beginning, the very first step at the gateway to the infinite cosmos.
When Batuta's 10 million year exploration at the heart of the Milky Way came to an end, the greatest challenge of the universe lay ahead, the intergalactic void. Batuta had never truly seen such emptiness before. It was mercilessly silent.
Even Batuta's own heartbeat seemed to be drowned out. This cosmic desert, spanning 2.5 million light-years, stretched between the Milky Way and its closest neighbor, the Andromeda Galaxy. The distance was so vast that even light itself had to travel non-stop for 2.5 million years to complete the journey. But for Batuta, time was no longer an obstacle. Tens of millions of years of experience had made it the universe's most patient traveler. Time, the greatest enemy of humanity, had become Batuta's most loyal friend, unconditionally by its side. Intergalactic travel was a new beginning of adventure for Batuta, because what awaited discovery in this void was even more fascinating than the most exotic phenomena of the Milky Way. Although intergalactic space may seem completely empty at first glance, it actually hosts some of the greatest mysteries of the universe. During the first 1,000 years of its journey, Batuta discovered lonely stars drifting in this void. These cosmic exiles, called intergalactic stars, were victims of gravitational battles between galaxies. Billions of years ago, they were ejected from their home galaxies during galactic collisions and now wandered alone in the endless darkness. Each of these cosmic exiles came from different civilizations, having lost their homes and paths in massive explosions, drifting through the deep cosmic night of the infinite void. Even more remarkable was the presence of planets orbiting these stars. Batuta discovered that some of these rogue planets still retain heat, and some might even harbor liquid oceans on their surfaces. This discovery turned all assumptions about the distribution of life in the universe upside down. Perhaps life did not develop in the bright arms of galaxies, but in these dark voids. After a 3 million year journey, Batuta finally began to enter the influence of the Andromeda Galaxy. This galaxy was much larger and far more intense than the Milky Way. Its central supermassive black hole was 100 times more massive than Sagittarius A star, and its surrounding accretion disk was so bright that it could be seen from millions of light years away. The light was impossible to ignore, so intense it nearly blinded Batuta's sensors, as if a cosmic beacon had been deliberately placed in the depths of the universe. Andromeda's spiral arms were far more active than those of the Milky Way. The rate of new star formation was 10 times higher than in our home galaxy. This also meant supernova exploded much more frequently. Throughout its journey, Batuta witnessed tens of thousands of supernova explosions, cosmic fireworks illuminating the surrounding light years. But the most striking discovery concerned Andromeda's fate with the Milky Way. Batuta's precise measurements confirmed that the two galaxies would collide in about 4.5 billion years. When these two titans entwined their predatory arms, they would perform a wild waltz, dragging millions of stars into their chaotic dance. This collision would fundamentally transform the star systems in both galaxies. Some would be flung into intergalactic space, while others would be drawn into the core of a new supergalaxy. The most terrifying phenomenon Batuta discovered in the outer regions of Andromeda were gamma-ray bursts. These cosmic disasters were the most intense events in the universe, releasing in a single second millions of times the energy produced by the entire Milky Way. To put this energy into perspective, a single gamma-ray burst wasted trillions of times the energy humanity has used throughout all of Earth's history in just the blink of an eye. Batuta had the rare chance to witness a gamma-ray burst firsthand. In the outer spiral of Andromeda, a giant star was taking its last breath. This star was 50 times more massive than the Sun, and its core was now filled with iron. Iron marked the final step of nuclear fusion. Heavier elements could no longer be produced. This meant a death sentence for the star. The collapse happened at about 10% the speed of light. The star's outer layers plunged madly inward, but the core became so dense it was even denser than a neutron star. A black hole was born. They say hatred is born from pain. Inside the black hole, this was true. The universe's most merciless predator, the black hole, was born from the corpse of a once brilliant star. Compared to its former self, it was now shrouded in the deepest darkness. Not only did it consume the matter around it, but it began warping space-time itself, swallowing reality whole. With its intense fury, it dragged everything along. The black hole's magnetic fields generated twin plasma jets shooting out in opposite directions. These jets were cosmic bullets, packed with gamma rays, traveling at speeds near the speed of light. Batuta was lucky the probe was not in the line of fire of these jets, otherwise its entire circuitry would have been instantly incinerated. GRB jets could shred anything in their path, down to the atomic level.
One of the greatest surprises of Batuta's journey through Andromeda was the discovery of the quasar at the galaxy's center. Quasars are energy monsters unleashed during the feeding frenzy of supermassive black holes. In other words, quasars were the black hole's prey, and the black hole exploited them like a cosmic vampire. The black hole at the heart of Andromeda weighed 200 million times the mass of the Sun. The accretion disk swirling around this colossal beast was so hot that its temperature reached millions of degrees. This heat kept atoms in a plasma state, and massive magnetic fields propelled this plasma out from two opposite poles at speeds near that of light. The result was plasma jets even larger than the size of Andromeda itself. Batuta dared to journey inside one of these jets. Traveling through a storm where thousands of cosmic ray particles struck every second and magnetic fields bent space-time was the most dangerous experience it had ever faced. Every second, Batuta faced the threat of disintegration, and a single miscalculation would have meant obliteration in the heart of the cosmic storm. Yet this ordeal provided Batuta with unique data about the true nature of quasars. After the Andromeda discovery, Batuta's next target was the other galaxies within the local group. Besides the Milky Way and Andromeda, there were about 50 smaller galaxies in this cosmic neighborhood. The Large Magellanic Cloud, the Small Magellanic Cloud, and the Triangulum Galaxy were among the largest of them. Each had its own unique story. The Large Magellanic Cloud was slowly being torn apart by the Milky Way. Gravitational interactions were pulling the stars of this small galaxy into the Milky Way's halo. In billions of years, it would be completely swallowed. The Large Magellanic Cloud had become a small prey, slowly digested in the jaws of a giant monster, losing a bit of its identity every day, stripped of its former glory inside the monstrous mouth. Batuta's exploration of the local group gave it the first clues about the larger structure of the universe. Galaxies were not scattered randomly, they formed a vast network. This structure, called the cosmic web, was woven from filaments of dark matter. This immense network made of invisible threads was now called the cosmic web. Galaxies caught in its grasp looked like particles of light. The space between galaxies was far from empty. Dark matter and dark energy filled these voids. Batuta began measuring the effects of these invisible substances. Dark matter was 5 times more abundant than normal matter, yet its nature remained unknown. Dark energy was driving the expansion of the universe, making up about 75% of the total energy mass content. These discoveries revealed to Batuta the future fate of the universe. Dark energy would prevail, pushing galaxies further apart. In billions of years, all galaxies outside the local group would disappear from sight, slipping beyond the cosmic horizon. The universe had been slowly abandoning its children to the ruthless darkness for trillions of years, and each galaxy was doomed to eternal loneliness. This truth only fueled Batuta's desire to explore further, for time was limited to unravel the secrets of the cosmos, at least on a galactic scale.
After 10 million years of exploration in Andromeda, Batuta faced perhaps the greatest mystery of the universe: absolute nothingness. There was nothing here. No sound, no light, no presence. It felt emptier than anything it had ever encountered before. This vast void stretching toward the Bootes constellation was an abyss 330 million light-years wide. Normally, there should have been about 2,000 galaxies in this volume, but only around 60 were found here. Known as the Great Nothingness, or more scientifically as the Bootes Void, it was one of the largest structures in the universe. For Batuta, entering this emptiness was like diving into the deepest trench of an ocean. But this time, instead of water, there was only the mysterious dance of dark matter and dark energy surrounding it. It felt as if it was sinking deeper and deeper, something pulling it down. Batuta was beginning to fade away.
Entering the Bootes Void, Batuta first noticed how different the rare galaxies here were. These cosmic loners, called void galaxies, were much smaller and contained far fewer stars than typical galaxies. While the Milky Way hosts around 400 billion stars, most of these galaxies had to make do with only a few million stars. Even more intriguing was their star formation rate. In normal galaxies, star production slows down as they age, but void galaxies became more active instead. Their solar waltz did not bring death, but life. It spread joy and restored vitality to their surroundings. But Batuta studied these strange galaxies for hundreds of thousands of years to understand why. The answer lay in gravitational interactions. In normal galaxy clusters, galaxies constantly interact, which can strip away gas clouds and suppress star formation. But the lonely galaxies in the void were spared such interference, allowing them to preserve their gas and continue slowly but steadily forming new stars.
During Batuta's journey through the void, the greatest discovery was the structure of dark matter filaments. These invisible threads formed the walls of the voids and explained why galaxies clustered in certain regions. It seemed that galaxies were trapped in this cosmic web, a dark matter skeleton woven like a giant spider's net across the universe. This cosmic web structure formed about 380,000 years after the Big Bang, when the universe first became transparent. At that time, dark matter had already started to clump together under its own gravitational pull. Normal matter was drawn into these dark matter wells, and over time, galaxies were born. However, in some regions, the dark matter density was below average. These areas became emptier as gravity pulled matter toward neighboring regions. The result was the formation of enormous voids, like the Bootes Void. Thus, the universe dragged its own children from their nests, condemning some regions to eternal solitude. After exiting the void, Batuta found itself in a completely different cosmic environment, the outskirts of the Virgo supercluster. This supercluster contained more than 100,000 galaxies, including the Milky Way. However, the real discovery made by humanity in 2014 was that even the Virgo supercluster was just part of a larger structure called Laniakea. Humankind, knowing only a small part of the universe, realized with this new discovery that they had been mistaken about their cosmic address. In reality, they lived in a much larger cosmic city. Laniakea, meaning immense heaven in Hawaiian, truly seemed infinite. Spanning 520 million light-years and containing 100,000 galaxies, Batuta observed how these galaxies flowed like massive rivers as it journeyed toward the center of this colossal structure. The source of these cosmic rivers was a mysterious region known as the Great Attractor. This immense gravitational anomaly was pulling all surrounding galaxies toward itself. It was as if a giant cosmic broom was sweeping galaxies toward its side.
However, the exact nature of the Great Attractor remained unknown. Because of the Milky Way's position, this region was hidden behind an area dense with stars called the Zone of Avoidance. During Batuta's journey through Laniakea, the greatest structure it discovered was the Shapley supercluster. Located 650 million light-years away, this colossal formation held the highest mass density known in the universe. It contained over 8,000 galaxies, and its mass was more than 3 times that of Laniakea. The Shapley supercluster was so massive that its gravitational influence extended billions of light-years beyond, even pulling Laniakea itself toward it. This discovery showed that the expansion of the universe is not uniform everywhere. This shattered all our previous perceptions. Now we had more knowledge about the universe, and our perspective was evolving and changing. As Batuta approached Shapley, it noticed how different the galaxies in this region were. Due to intense gravitational interactions, most galaxies had transformed into elliptical shapes. Their spiral arms had disappeared because of continuous collisions and mergers. These galaxies had long since ceased star formation and were now slowly aging.
During Batuta's supercluster journey, its most valuable discovery was mapping the tiny fluctuations in the cosmic microwave background, CMB radiation. This radiation was essentially a snapshot of the universe just 380,000 years after the Big Bang. In other words, it could be called the universe's baby photo. Every pixel in the image represented fluctuations created by billions of galaxies. The temperature variations in the CMB showed differences of only about 1 part in 100,000. However, these tiny fluctuations were the seeds of all cosmic structures we observe today. Batuta's sensitive sensors measured these variations in unprecedented detail. The most striking discovery was an anomaly in the CMB called the cold spot. This cold region was about 70 microkelvins cooler than the average and spanned 1.8 billion light-years. The source of this anomaly remains unknown. This cold spot, resembling a scar on the face of the universe, was so mysterious it drove cosmologists to the brink of obsession. It triggered numerous further research efforts. Some theories suggested it was evidence of a collision with parallel universes. Others thought it was the effects of the largest known cosmic void. Batuta made a careful deviation of 500,000 years in its observations to study this cold spot in detail. After its supercluster discoveries, Batuta encountered the universe's largest structures, the Great Walls. These colossal chains of galaxies stretched for billions of light-years and formed the very skeleton of the cosmos. These massive walls, as if built by the hand of a god, surrounded us like the walls of a fortress, clearly defining the boundaries of the universe. The most famous among them was the Great Wall of Galaxies, also known as the Coma Wall, measuring 500 million light-years long, 300 million light-years wide, but only 15 million light-years thick. This structure was one of the largest coherent formations in the universe. Later, the Sloan Great Wall was discovered, spanning an even more staggering 1.37 billion light-years in length. As Batuta traveled through these walls, it observed how galaxies were strung like beads along dark matter filaments. Each filament acted like a massive cosmic pipeline feeding galaxies over billions of years. Yet in some regions, this feeding system had been cut off, triggering a process known as galactic strangulation.
During Batuta's discovery of the large-scale structures, the most surprising finding was that the voids were not completely empty. Inside these immense cosmic gaps lay extremely ancient galaxy remnants and structures known as fossil groups. This discovery was crucial for us because these massive fossils were like photographs from the past, and it seemed that for millions of years, fossil skeletons of forgotten civilizations quietly rested in the deepest corners of the cosmic graveyard. These fossil groups were once galaxy clusters that had transformed into a single massive galaxy after the central galaxy swallowed the others. The hot gas halos surrounding them were the only evidence of their once crowded past. Even more mysterious was the expansion rate of the voids. The effect of dark energy was stronger in these empty regions, causing voids to grow faster than the normal expansion of the universe. This meant that in the future, most of the universe would become completely empty. According to Batuta's calculations, in 100 billion years, 95% of galaxies would fall into void regions and be left isolated billions of light years apart from each other. In other words, the universe would bury its children one by one randomly into darkness. Each galaxy would struggle to adapt to a foreign environment, with no one around to hear their voices. This reality reminded Batuta how precious time truly was, and guided it toward even farther, the universe's most mysterious regions.
Batuta, having traveled billions of light years, was now in pursuit of the oldest secrets of the universe. The anomalies in the cosmic microwave background had given clues about the birth of the cosmos, but the real answers were hidden much deeper, woven into the very fabric of space-time itself. He was no longer merely chasing matter, he was chasing truths, probing the deepest traces of the universe like a cosmic archaeologist. His first target was to find the mysterious structures that theoretical physicists called cosmic strings. These cosmic threads were thought to be remnants of phase transitions that occurred just moments after the birth of the universe. If they truly existed, they would hold priceless information about the earliest moments of the cosmos. In Batuta's memory was the revolutionary discovery made in 1979 by young physicist Alan Guth at MIT. While trying to solve some fundamental problems in the Big Bang theory, Guth proposed a process called inflation that occurred immediately after the birth of the universe. That night, the calculations in Guth's notebook would lead to a result no one could have predicted. With just a few lines of math, he had unlocked the secret of the universe's birth. A few mathematical equations opened the lock to the 13.8 billion-year-old mystery. This is why mathematics is mysterious. It holds countless secrets waiting to be discovered. The inflation theory proposed that between 10 to the negative 36 and 10 to the negative 32 seconds after the Big Bang, the universe expanded trillions of times, from a region smaller than a proton to the size of the observable universe. This expansion was so rapid that it exceeded the speed of light by trillions of times. However, this did not violate Einstein's theory of relativity because it was space itself that was expanding. Nothing inside it was moving faster than light. This process solved the three key problems: the flatness problem, why is the universe geometrically flat? The horizon problem, why were regions on opposite sides of the universe at the same temperature? And the monopole problem, why have no magnetic monopoles ever been observed? Batuta began studying the oldest structures in the universe to find evidence that would confirm this theoretical framework. The greatest miracle of the inflation process was that it magnified the microscopic fluctuations from quantum mechanics to cosmic scales.
Like the butterfly effect, where the flap of a butterfly's wings can cause a storm on the other side of the world, these tiny tremors, smaller than an atomic nucleus, became giant waves that determined the fate of billions of galaxies. The faint whispers of the quantum world transformed into the grand symphony of the universe. This process allowed completely random quantum events to become the seeds of all the cosmic structures we see today. As Batuta examined the temperature fluctuations in the CMB, it could detect these quantum origin patterns. Every small temperature difference was a trace of a quantum event that happened 13.8 billion years ago. The statistical distribution of these fluctuations perfectly matched the Gaussian distribution predicted by inflation theory. However, what Batuta was searching for were anomalies outside these smooth patterns. Because during the inflation process, some exotic structures might have formed: cosmic strings, domain walls, and textures. These structures, called topological defects, were the remnants of phase transitions. After 200 million years of systematic searching, Batuta finally found its first cosmic string. This structure was billions of times thinner than a human hair, yet its length stretched across intergalactic distances. How could such a thin formation travel billions of light years without damage? The amount of energy concentrated in the string was incredible. Just 1 centimeter of it had a mass equivalent to that of Earth. This cosmic string warped space-time so powerfully that light rays passing nearby were distorted. Batuta mapped the string's properties by using this gravitational lensing effect. The string slowly vibrated, producing gravitational waves, ripples in space-time, predicted by Einstein. The most astonishing discovery was that over time, the string would self-intersect and break into smaller loops. These loop structures lost energy by emitting gravitational waves and eventually evaporated completely. These incredibly thin strings, which had clung tightly to existence since the very beginning of the universe, gave their final breath when their time came, disappearing entirely from reality.
Batuta's discovery of cosmic strings provided invaluable insights into the phase transitions that occurred in the early universe. These processes were like water freezing into ice, but on a much more fundamental level. As the universe cooled, different physical laws emerged through symmetry-breaking processes. The first major phase transition happened around the Planck time, 10 to the negative 43 seconds. At this moment, quantum gravity separated from classical gravity, and the concepts of space and time were born. From nothingness, reality emerged at the Planck time. The first coming into existence from non-existence occurred at this moment. Would other voids in the universe come into being when their time arrived? However, our knowledge of this process remains very limited because we still lack a complete theory of quantum gravity. The second major phase transition was a separation of the strong nuclear force from the other forces, 10 to the negative 36 seconds. During this process, some cosmic strings may have formed. The third transition was a separation of the electromagnetic and weak nuclear forces, 10 to the negative 12 seconds. This last transition has even been recreated in particle accelerators at CERN. One of the most fascinating phenomena Batuta discovered was a process called false vacuum decay. The Higgs field, predicted by Peter Higgs in 1964, existed as an invisible field spread throughout the entire universe. This field, which can be imagined as an invisible ocean, carefully filled every corner of the universe. As particles swam through this ocean, they gained their masses. This field gave mass to particles and broke the unification of the electromagnetic and weak nuclear forces. However, the current value of the Higgs field might not be the true ground state. If the field were to transition to a lower energy state, a vacuum decay would occur, causing all the physical laws in the universe to change. This process would happen in the form of a bubble expanding at the speed of light, and everything caught inside this bubble would be subject to completely different physical laws. Batuta searched for signs of this vacuum decay in various regions of the universe.
Unfortunately, such a process had not started yet. However, quantum mechanics predicted that such an event would eventually happen, perhaps trillions of years from now. Besides cosmic strings, Batuta also discovered other topological defects. Domain walls were two-dimensional structures that could separate large regions of the universe. These invisible walls spread across every corner of the universe, acting as boundaries between different physical laws. That's why these structures were far more dangerous than cosmic strings, as they contained much more energy. Fortunately, the observable universe did not support the existence of such domain walls. If they did exist, they would prevent the universe from expanding. This ruled out certain symmetry-breaking models and helped physicists refine their theories. Textures were three-dimensional defect structures. They were usually unstable and quickly dissolved, but during their decay, they produced strong gravitational waves. Batuta searched for traces of these structures in the mass distribution within galaxy clusters. During his search for cosmic strings, he also looked for traces of models that were alternatives to the standard inflation theory. The ekpiotic model proposed that the universe was born from the collision of two giant brains in higher dimensions. As these two giant brains collided, particles scattered through cosmic space like rain. This model could explain the flatness and homogeneity of the universe without the need for inflation. Even more radical was the eternal inflation theory. According to this model, inflation never stopped. New universe bubbles were constantly forming. Our universe was just one of these endless bubbles. Each bubble could have different physical laws. Batuta searched for the traces that collisions with neighboring universe bubbles would leave on the CMB. Such a collision would create giant ring-shaped anomalies in the sky. Although he had not yet found definitive evidence, he had detected some suspicious signals.
At the smallest scales, at the level of the Planck length, 10 to the negative 35th meters, space-time itself was thought to be foamy, made up of tiny bubbles. Each tiny bubble was assumed to be a mini-universe, and the bursting of one of these bubbles meant the birth of new dimensions. This quantum foam was an environment where pairs of virtual particles were constantly coming into existence and then vanishing. Batuta's ultra-sensitive sensors attempted to measure the macroscopic effects of these quantum fluctuations. It tested whether beams of light experienced minute delays as they passed through this foamy structure. The results suggested that space-time might indeed be discontinuous at the smallest scales. These discoveries supported quantum gravity theories such as loop quantum gravity and causal dynamical triangulation. According to these theories, space-time is not continuous, but discrete, like a digital pixel structure. Batuta's findings led it to investigate cosmic strings in greater detail, as these structures not only provided clues about the universe's past, but also held promise for future technological possibilities. Perhaps following these cosmic strings would lead us to the secrets of the universe, making them worth pursuing.
We had never encountered anything like this before. We knew of substances with extremely high density, but this one was so heavy that a 1 centimeter piece outweighed an entire city. This meant it surpassed the known physical limits of matter. The probe's remote sensors began mapping the distortions in the fabric of space-time surrounding the string. As beams of light approached it, they bent. The flow of time slowed down, and in some regions even reversed. This phenomenon hinted at what theoretical physicists call closed time-like curves, regions where time travel could be possible. In these points, time behaved strangely. So far, there was no clear evidence beyond time slowing down or speeding up. No confirmed link between past and future had been observed. If you had the chance to manipulate time, would you go to the future?
or the past. The cosmic string also stored an immense amount of energy. According to theoretical calculations, when a cosmic string vibrates, it could release energy in the form of gravitational waves powerful enough to shake the entire universe. Detectors like LIGO and Virgo were attempting to capture such vibrations, but no definite signal had been detected yet. For Batuta, the real question was this: could this ancient structure hold the key to humanity's survival? When the probe's creators sent it, they were searching for a glimmer of hope at the very edges of the universe, where the limits of physics were tested. Perhaps the warped space-time around the string contained gateways to other dimensions. Perhaps it could reveal a way for humanity to escape a dying solar system. Batuta pursued these mysteries like a detective. It had to gather as much information as possible because every piece of knowledge could be crucial to the survival of the human race. During the probe's approach, the magnetic fields surrounding the cosmic string began to behave in strange ways. These fields spiraled along the string, accelerating charged particles to incredible speeds. The resulting particle streams acted as a natural particle accelerator, producing energies millions of times greater than those of the LHC. Batuta's advanced artificial intelligence, while analyzing these observations, reached a startling conclusion. The cosmic string was not only bending space-time, it might also contain intradimensional connections predicted by the multiverse theory. Modern physics approaches such as string theory and M-theory suggest that our universe exists on a three-dimensional brane and could be connected to other universes in higher dimensions. I have always thought of the multiverse theory as the idea that the world we live in is the result of the choices we make, but this seemed to be far more than that. The probe's final decision was approaching. Diving into the cosmic string might mean losing all sensor data, but such a sacrifice might provide the crucial knowledge humanity needed for its future. Batuta decided to send one last message to its creators. I stand at the threshold of the deepest secrets of the universe. This knowledge may be essential for you. I speak to you from beyond the stars. Do not lose hope. By the time the message reached Europa, Batuta would already have plunged into the space-time tunnel twisted by the cosmic string. This final mission was not just a sacrifice of a probe, but also the triumph of science and curiosity. Humanity, by reaching the farthest edges of the universe, had succeeded in surpassing its own limits.
Batuta's final signal to humanity, sent with his last breath, revealed the truth both terrifying and mesmerizing. When the signal reached Europa, the remaining representatives of humankind were confronted with one of history's deepest questions. How will the universe end? Billions of years of exploration had brought not only a catalog of distant galaxies and exotic phenomena, but also clues to the cosmos's ultimate fate. The second law of thermodynamics tells a harsh truth about the destiny of the universe. Entropy always increases. When this simple yet profound principle was formulated by Rudolf Clausius in the 19th century, it merely explained the efficiency of steam engines. But when applied on a cosmic scale, it foretold the end of the universe. Every energy conversion, every shining star, every chemical reaction was dragging the cosmos toward the final state known as heat death. Batuta's observations showed that this process had already begun. The rate of star formation had passed its peak, and the universe was now producing fewer new stars. Long-lived stars like red dwarfs would continue to burn for billions of years, but even they were not eternal. The universe was slowly aging, signaling the end of its youth because it had begun consuming fewer and fewer stars. Scientists had grouped the possible futures of the universe under three main scenarios.
the Big Crunch, the Big Rip, and heat death. The data gathered by Batuta confirmed that dark energy was still being observed and that the universe's expansion was accelerating. This pointed to heat death as the most likely scenario. In this scenario, the universe would continue to expand forever. Galaxies would drift apart, stars would burn out and grow cold, and ultimately all matter would decay into fundamental particles through proton decay. In the end, only black holes would remain, and they too would evaporate through Hawking radiation. The universe was slowly preparing for its end, gradually ceasing to breathe, yet continuing to shine until the last light faded, until no energy remained to emit its glow. Then it would be buried in darkness, just as it had buried its own children. But the cosmic thread Batuta had discovered might have the power to change this bleak picture. According to multiverse theories, cosmic strings could act as bridges between different universes. Perhaps it was possible to cross from dying universes into young and vibrant ones. This idea lit a new spark of hope for humanity. Modern physics approaches such as string theory and M-theory suggested that reality was far more complex. In 11-dimensional space-time, our universe existed on a 3-dimensional brane. Countless parallel universes could exist in the other dimensions. If we imagined our universe as a single page, it could be just one page in a vast book, while the other pages held countless parallel universes.
Carl Sagan's famous words became even more meaningful in this context. The cosmos is within us, and we are within the cosmos. Humanity, though physically limited, could reach the farthest corners of the universe through its consciousness and curiosity. Probes like Batuta had become the cosmic legacy of humankind. As the scientists on Europa analyzed Batuta's final data, they were also taking a journey into the past. Humanity's space age had begun in 1957 with the launch of Sputnik, reached its peak with the Apollo program, and then extended into interstellar space with the Voyager probes. Every step had been a triumph of curiosity and the desire to explore. And every launch had allowed humankind to reach another corner of the cosmos. Perhaps the most important discovery was how rare and precious life itself truly was. The Fermi paradox, if the universe is full of life, then why don't we see anyone, remained unanswered. Batuta had passed by billions of planets, but found no sign of life. This could mean humanity was the only known intelligent species in the cosmos. This reality created a profound sense of loneliness, but it also carried a tremendous responsibility. Humanity was not only the guardian of its own kind, but perhaps the sole conscious being in the entire universe. Every human death, every lost culture, was an irreparable loss on a cosmic scale. Of course, the possibility that life exists in regions we cannot reach also comes to mind, and this is quite reasonable. Wouldn't it be foolish to say there is no life without having fully explored the universe? Concepts like Dyson spheres, proposed by Freeman Dyson, suggested that advanced civilizations could harness the entire energy output of their stars. Perhaps humanity could find ways to escape the deadly sun and establish new homes around red dwarfs. Since these stars burn for trillions of years, they could provide almost infinite time for civilization. The strange world of quantum mechanics offered even more radical possibilities. Thanks to quantum tunneling, orderly structures could spontaneously emerge despite the second law of thermodynamics. The Poincaré recurrence theorem suggested that given infinite time, the current state would eventually reoccur. This meant that even billions of years from now, life could somehow be reborn.
Of course, this was according to the point-Carré recurrence theorem, but we had no intention of gambling our future away. That's why we were striving to do far more than what was merely possible. As Batuta's story came to an end, another story was actually beginning. The probe's discoveries had become not just a catalog, but a legacy for future generations. The children of Europa would grow up, develop new technologies, and perhaps unravel the secrets of the cosmic threads. Maybe they would test multiverse theories and find ways to cross from dying universes into those brimming with life. Carl Sagan's message on the Voyager Golden Record was still relevant. This is a gift from our world. Sounds of our music, our science, our thoughts, and our feelings. Batuta carried a similar message, but this time it was composed not just of sounds and images, but of the deepest secrets of the universe. Although the ultimate fate of the cosmos remained uncertain, one thing seemed clear. As long as humanity's desire to wonder, explore, and understand could surpass physical limits, our species would find a way to endure. Perhaps our bodies would decay and our planets would vanish, but our thoughts and discoveries would continue to echo through the cosmos forever. If you enjoyed Batuta's final journey, don't forget to subscribe. These videos are made with an incredible amount of effort and go through extensive research. Your support means the world to me. Thank you in advance.